Hello statistics students, my name is Jami Emigh, and this video will start our discussion on Chapter 9, Inferences from Two Samples. Section 9.1, we're going to look at the difference between two population proportions. So the word two in these titles is new. Everything we've done up until this point has been based off one sample, and Chapter 9, we're going to start to look at two samples. What I mean by that is, here's an example. A drug manufacturer claims that subjects treated with Lipitor have a mean cholesterol level lower than the mean cholesterol level for subjects given a placebo. That situation we can divide into two populations. Population number 1 would be the cholesterol levels for the subjects treated with Lipitor, and then population 2 would be the cholesterol levels for the subjects treated with a placebo. So we're going to compare those populations. Now, as far as symbols, good news. Population number 2 uses the same symbols. The only difference is you'll see subscripts now of 1 and 2. For example, you might see P hat sub 1. That would now mean sample proportion from the first population. And if you see a P hat or any symbol with a sub 2, these subscripts, they don't mean anything computation-wise, numerically. They're just a way of naming or communicating to us that this is from population number 1 and this value would be from population number 2. Requirements. We need proportions from two independent simple random samples, okay? Population 1 needs to be independent of population 2, and we still need simple random samples for each. Furthermore, we need each sample's number of successes to be greater than or equal to 5, and the number of failures to be greater than or equal to 5. So basically, you don't want to compare two populations where, let's say, population number 1 just failed at everything. Say it had like 0 successes. 0 successes. I'll stop there. 0 successes. It wouldn't make sense for us, and we can't use these programs to compare two populations that don't at least express some level of success and some level of failure. And the bar for that is set as 5 or more successes and 5 or more failures for each population. Then we can compare the two using the difference between two population proportions. All right, what we're going to do is check if P sub 1, that's population proportion from population number 1, less the population proportion for population number 2 is equal to 0 or not. Another way to read this right here would be that their difference is 0 if P sub 1 minus P sub 2. So if their difference is nothing, we're going to check that. Therefore, we will look to see if our interval contains 0 to help us make our conclusion. Okay, what we mean by that is, let's say we have an interval like this here. Let's say the interval starts at a negative value, and let's say the interval ends at a positive value. Then these two limits right here, this interval right here, 0's included in there. It's the only way, because you start at a negative, you end at a positive. So somewhere along this path, in this interval, you'll find 0. So this is a nice note. If your limits have different signs, for example, 1 negative and 1 positive, then your interval contains 0, and we're going to say, well, if it contains 0, that means that there is no difference in the population proportions. Here's the other case. Your limits have the same signs. So that would be if they're both negative or if they're both positive. In that case, you can imagine your number line. If the limit starts at a negative and ends at a negative, it does not include 0. And if your interval starts at a positive and ends at a positive, it does not include 0. So in that case, we would conclude that the two population proportions, there is a difference. However, of course, do not forget to consider practical significance as always throughout this course. For StatCrunch, 2 populations, hypothesis test, and confidence intervals. All right, we need to make sure that we have 2 independent population proportions, and we're going to look at their difference. We're going to open StatCrunch, same stat drop-down menu, and check this out. We're going to run proportion stats. We've used this program before, except when we used it, the next menu we selected, menu item, was 1 sample. But now in Chapter 9, we're going to go proportion stats 2 sample. It's going to be from with summary. We're going to let the program know the number of successes for population 1 and 2, the number of observations for population 1 and 2, and then we will have to let the program know what we are trying to accomplish. So if the question or our task at hand is to test a hypothesis, then at that point you need to tell the program, okay, we're going to do a hypothesis test. But if our task is to set up a confidence interval, then we got to tell the program, okay, confidence interval. So after this right here, you'll have to decide. And you don't actually have to decide, you just have to read the directions carefully on what the task is and then tell the program which one. If it's a hypothesis test, we'll set up the null and alternative hypothesis, click Show Critical Values, enter our significance level as a decimal, compute, and then to make our decision, we can compare the p-value to the significance level, just like we did in Chapter 8, the p-value method. Now, if we're setting up a confidence interval, we're going to have to tell the program what level of confidence we want, make sure we enter it as a decimal, we'll hit compute, and then what we're going to do is look at the signs, the negative versus positive. We want to look at the signs for the lower and the upper limits, and just like on the last slide, if they are opposite signs, then 0 is between them, and we conclude no difference, okay? Opposite signs, no difference. If the signs are the same, then 0 is between them, and we report there is a difference. Same sign is a difference. Okay, summary. Opposite signs, no difference. Same signs, difference. All right, let's try one. Example A. 89 undergraduates were randomly assigned to 2 groups and given a choice to keep the money or they could buy gum with that money. Part A wants us to test the claim that money in larger denominations is less likely to be spent relative to an equivalent amount of money, but in smaller denominations. They want us to test that with the 0.05 significance level. All right, let's check out the summary we've got here. We had, let's check this one out. Lowercase n sub 1, that is the size, the sample size of population 1. So there were 46 people in this group, and those 46 people were given a $1 bill. Okay, and it turns out that 12 of those 46 spent the money. Okay, that's interesting. So given a $1 bill, 12 out of those 46 spent the money. Check out population 2. Sample size is 43. They were not given a $1 bill. They were given 4 quarters. That is an equivalent amount, but in smaller denominations, quarters versus dollar bills. In that situation, 27 of them spent the money. So it's very interesting here that it looks like less people spent the money when they were given the higher denomination, and more people spent the money when they were given quarters. I'm sure each of those subjects had their reason for it, so we want to check what's the population proportion. How do we compare the two? So we are asked to test the hypothesis, so we need to set up our null and alternative hypothesis. Okay, notice this time for Chapter 9, slightly different. For Chapter 9, we're not comparing just a single p or proportion to a value. We're not doing that in Chapter 9. In Chapter 9, we're comparing 2 proportions, one from each population. So population 1 set equal to population 2, And the alternative hypothesis comes from the stating of the claim, words in the claim right here. Less likely. That's where we got the less than sign from. So population 1 is less likely to spend the money compared to population 2. All right, we need to run this summary through our technology. Let's go to StatCrunch now. Okay, here in StatCrunch, we go to Stat, Proportion Stats, not one sample, that was Chapter 8, 2 samples for Chapter 9, and we weren't given the data, we were given a summary of it. All right, number of successes for population 1, 12 people spent the money out of, there were 46 in that group. Number of successes for population 2, 27 spent the money, there were 43 in that group. I can show you what that looks like when we get back to our notes. Okay, click Show Critical Value, significance level was 0.05, and we hit Compute. Okay, output screen looks really similar to Chapter 8. We've got a p-value here that we can compare to the significance level. If they ask us the critical value, we've got it, 1.96. If they ask us the test statistic, we've got it, negative 3.49. But in this particular problem, we're just going to take the p-value, 0.005, and compare it to the significance level. Let's go back to the notes. Okay. Let's finish this question and then I'll show you how if you manipulate these, it'll look like it was on the input screen. Okay, first though, let's stay on track. P-value was 0.0003, but accurate to 3 decimals. Should that be the task or the request? It's just 0.000, and that's okay. We know that that just means it's a very small p-value. And it is less than our significance level of 0.05. The rhyme can be helpful here. P is low, the null must go. So we reject the null hypothesis. And then when we write our conclusion, we say that there is. Just like in Chapter 8, remember that reject goes hand in hand with the word there is. Had we found that P was high, our decision would have been fail to reject the null. And right here we would have said there is not sufficient evidence. Okay, to support the claim that there is a difference, for ours though, there is sufficient evidence to support the claim that there is a difference in the 2 population proportions, who would spend the money. I could see that. If I was given 4 quarters, just for the sheer inconvenience of carrying 4 quarters around, I might spend it versus the dollar. It depends. Part B. Would a 95% confidence interval support our hypothesis test conclusion? Okay, the answer should be yes. It doesn't matter if you're running a hypothesis test or setting up a confidence interval. We should get the same conclusion, but let's check just to make sure. Would a 95% confidence interval support our hypothesis test conclusion? Okay, all right, we don't need to retype everything in. We can just go right here to where it says options. We'll edit it. And we'll just ask the program to change the task, which is right here. Click right here, okay? We want to check the confidence interval now. And compute. Okay, this is the output screen for a confidence interval. We saw these a lot in Chapter 6. And we have our lower limit here and our upper limit right here. All right, you guys. Check the signs. Remember, we're checking to see if these are both negative, both positive, or if they have opposite signs. That's going to lead us to our conclusion. Okay, both of these are negative. Lower limit, negative 0.56 or 559, however many decimals requested. Upper limit, negative 0.175. Okay, I'm going to write those limits in interval notation. So opening parentheses, I put the lower limit, comma, and then we put the upper limit and we close with parentheses. These are the same sign. That means 0 is not in the interval. 0 is not in this interval. That means that there is a difference. Here it is written out. Same sign, interval does not contain 0. We report that there is a difference between the two proportions, which is what we said with the conclusion for the hypothesis test. Okay, I want to show you, make sure you guys see this little algebraic manipulation. This is what it looks like for us. Whoever wrote the program has it just solved for 0. So if you subtract p sub 2 from both sides of the equal sign, subtract p sub 2 from both sides, then your new equation, some different form, would be p sub 1 minus p sub 2, and it's equal to, and over here on this side of the equation, we would just have 0. So that's how it looks in the program. This is how we write it. They are equivalent. Just remember your algebra skills. We just moved the p sub 2 to the other side of the equal sign to solve for 0. Let's try another one. Test the claim with a 0.01 significance level that a higher proportion of students who take statistics in 8 weeks, meeting 4 days a week, successfully pass the class than students who take statistics in 16 weeks, meeting 2 days a week. Okay, got two populations here. We've got 8-week stat students. Looks like we had 75 of them. 48 passed. We have another population of 16-week stat students. There were 80 of them, and 43 passed. All right, what's our task? Test the claim. So we'll set up our null and alternative hypothesis. Always equals for the null. And for the alternative, got to read that wording carefully, level that a higher proportion. That's the inequality wording right there, you guys. Higher. That's what told us to use the greater than sign right here. All right, let's run this summary through StatCrunch. Just gonna edit. We had 48 passed the class out of, it was 75 taking the 8-week class, and 43 passed. We had 80 of them taking that. We'll switch this back to hypothesis test. It was claiming that the proportion was greater and significance level was 0.01. Compute. Here's our p-value, 0.0976. Let's put that back in our p-value of 0.0976 compared to this significance level. P is high. The null will fly, so we fail to reject the null. Whenever we decide fail to reject the null hypothesis, we say there is not sufficient evidence to support the claim that there is a difference in the proportion of students who pass the class in 8 weeks or 16 weeks. All right, part B. Construct a 99% confidence interval to support the hypothesis test. Notice here, guys, for part A, we had a significance level of 0.01, which goes with the confidence level of 0.99. They're complements of each other. All right, let's go back to StatCrunch and run a confidence interval performance instead. Just go to Options and Edit and change the task right here. Update that confidence level. And we're good. Compute. Lower limit, negative 0.999841335. Upper limit, positive 0.3049814. All right, so we have a negative, we have a positive. In interval notation, we'll write that as negative 0.1 to positive 0.305. those have different signs. That means that our interval does contain 0. We will report that there is not a difference between the two population proportions, and that supports the conclusion that we got from part A using a hypothesis test. All right, let's take a break. My name is Jami Emigh. Next time I see you, we'll talk about section 9.2. Have a good day.